Hello everyone, it's July the 3rd, Saturday. Well, before we start, I want to say this morning I cooked some pig in blanket, vegan style, Chinese style as well. I used some Chinese pancake and some incognito sausage. I rolled them up, put a toothpick through it. Damn, that one was pretty delicious. So we had that and pretty content and ready to rock and roll. Today is going to be difficult. So I'm having a new plan. It's every Saturday now I spend a lot of time just trying to figure out. Sometimes I can't after a couple of hours. But today, oh, what I do? So today the hope is 1 hour. All right, so today the goal is to spend 1 hour on it. If I cannot solve it, I'm gonna call it quits. Well, I'm gonna say it this way right now, but I'm pretty sure I won't do it. All right, take a look. Max sum of rectangle no larger than k. Okay, it's a rectangle. Given a m by n matrix and an integer k, return the max sum of a rectangle in the matrix such that the sum is no larger than k. It is guaranteed that it will be a rectangle with a sum no larger than k. The max sum of a rectangle has a sum no larger than k. So given a matrix, k is 2. So we want to find a max sum of a rectangle. What do you mean max sum? So 2 is the max number no larger than k. So this one will be the entire thing. What if the number of rows is much larger than the number of columns? Wait, what do you mean? This has no condition on what if the number of rows is much larger than the number of columns? We just swap it, it will be the same thing. Anyway, let's take a look. So we want a rectangle. So it could be that could be a rectangle, right? This could be a rectangle. This could be a rectangle. At least one rectangle with sum no larger than k. 2 is the maximum, so what we're gonna return is the sum, right? Return the max sum. So we just search through the rectangles and look for the sum and see. We can see if we can get a k. If we can get a k, then we have the result. If we cannot get k, k minus 1, k minus 2, the value is this, k is this. Oof. I remember last time something similar, we used cumulative sum, prefix sum, and two sum, right? So I remember, I don't remember very well, but I remember it is possible to get any size with ease. How do we do it? I think it's a cumulative sum on a row, and we do also on a column. Hold up. Let me write it out. So we say cumulative sum on a row, like 1, 1, 2, and on a column we add on the top. So each value will be the sum of the 4, right? So this one will be 1, and this one will be minus 2 plus 1 will be 1. Yeah, and this one will be 3 plus 2 will be, that's not correct. We add it to the top. No, we not only add to the top. Hold up. That is going to be minus 1. It's not 1. It's going to be minus 1. So minus 2 plus this, because this is the entire thing. Oh, we didn't do first round. Okay, my bad. We're gonna do 2 rounds. So we're gonna hold on. So we're gonna do a cumulative sum first, and then 1, and then we add it to the top, and then that's gonna be 1. All right. So this is the same. We're gonna add to the left. Yeah, we add to the left cumulative sum, and then we add at the top. So it's 1, that's going to be 3. Yes, that's 3. So each one represents the entire thing. This one represents the entire thing. This one represents the entire thing. So for any rectangle, we're going to take this and minus the so for anything, so we're going to take this value minus the top and minus the left. Okay. So we can build it up. That's going to take on to build each row. On times m. Yes. OMN to build up this, and then we need to find the sum. How do we find the sum? So basically what we're just saying, the max sum. Can we add some dummy so they will always be the same? What if we add a dummy, and on the dummy it's so like if we want to know this, it's gonna be this, right? Minus this, and plus this. So the dummy is all going to be 0, right? So this, we want to know this, just going to be this minus this minus the 1. Hold on. So this and minus the 1 ahead, right? Which is this thing, and minus the 1 here, and then plus this. Then we can unify the whole thing. Let's add 1 row, add 1 column at the top. Okay, in that case, if we want to say we have a 3, the maximum, so we go for the max value. Now we have a k, so we know k, right? We can just go through the entire thing. Oh, we can go through the entire thing and compute every single No, that's not likely. How can we cannot compute every single possibility, because anyone hold up. Anyone, if we have a k, so if we don't compute this one, it's going to be 3, right? Minus 0 and minus 3 is going to be the entire thing, minus this and minus this, right? Now this is actually 1, my bad, this is a 1, this is a 1. We have to add to the top. Yeah. 1, 3 minus 1, so this is 2. So here is 2. So on here, so minus this plus this is a 0. What is the largest sum? Even if we compute this table, if we want to try every single one on every row, right? We'll try every single one on every row. We're gonna have to try every single one, right? This have to try every single one. I mean, one thing we can do is as we go through, if we find a value that is equal, it's actually here we can only return, right? As we are building up, as we're building up the 2D prefix array, we can say if we encounter k, we return k immediately, right? We return k immediately. If we have not found a k, let's say we found a k minus 1, and how do you know there's no other k? Because, yeah, like if you find it, that's good, right? If you don't find it, or like if you find anything that's slightly bigger than k, right? If you find it's bigger than k, then you just try to search. Try to search through, like if I have a 3, right? So the k is 2. If I have a 3, then what I want to do is to see if there exists a 1 on one of the rows and columns that I need to remove, right? So we can remove it. If the first one is 1, so we always trying to remove. We have this, and we also remove this one, and remove this one. Right, so we just go from here, one by one, to see if there's anyone that, which means we can put. Hold on. So as we're going through, we go by row, right? As we're going through the row, we put all the values that have been encountered in, like say, in a set, right? In a set, and then we're not returning any concrete structure. We just want to return the maximum sum that is no larger than k. So we go through each value. If it's smaller than k, then we put it in a set. If it's equal to k, we return immediately. If it's larger than k, then we search through the previously encountered value to see if we can find one that can make the value to k, right? Or to, not really to k, or to just some values. Hold on, let me think. So we are here, right? And then we can remove this, or we can remove this, or we can remove this. So we can remove 2 and plus 1 more. Maybe all we need to do is remove 1, right? Because if you want to calculate any rectangle, you need to remove 2 times and plus 1 time, which means I'm going to remove 2 times. Minus 1 now will become smaller, then I plus 1 time, and it might get bigger. Is that worth it? Maybe that's not even worth it, because if I just remove once, and let's say it's just the sum of this, so we only calculate the sum, every step, we only calculate the sum of columns, right? Of the columns. That's what we're trying to do. We calculate the sum of the columns, and we want to see if it fits. I mean, we can also calculate the sum of rows, but if we want to calculate the sum of rows, that's possible for each one. So the worst case is that we calculate the sum. So it's column, so that's going to be OM, and each one is going to go be OM. That's going to be very expensive. I don't think that's the solution. I don't think that's going to be the solution. So we go each column, I remove it. Let's say I compute a sum of this, sum of this, sum of this. So from a smaller one going big, we do capture all the columns. And the reasoning is if a column, but the matrix value can be negative, right? So if it's going to be negative, that means we might miss, right? We might miss. If we get the maximum values, if we get the values for each, or we don't get the values, how? Hold on, let me think. I mean, I feel like this is not sufficient. Because if we find k, then we return. If we cannot find k, right? If we cannot find k we might find k if we do like rows. I don't know. I feel like the best strategy, the 100, maybe that is like we have to find every single one, right? Which means as we go through each row, right? Go through every element, the prefix sum, go to each row, and each one we have to iterate through all the rows and columns that we have seen before, and basically calculate all the possible rectangles, that including the new one, right? Including the new one, and yeah, I have to go through every single one and keep track. We'll put everything. Dang, that's gonna be huge. We keep everything. No, we just need to keep no, we need to keep we keep track of the largest value that is smaller than k. And if we encounter k, then that's good. If we don't encounter k, we have to keep going. What's the runtime? Man, the runtime is m times n is to build, right? And for each one, we have to go through m and n again. Let's try. Maybe this, because we're talking about 100 by 100, right? So maybe we can squeeze in, right? Maybe we can squeeze in. All right, let's take a shot. All right, let's take a shot at this. So the ideal is we're gonna first build a matrix. So we're gonna say prefix sum, right, equals m n equals len matrix, that's the row, and len matrix 0, that's the column, right? And then we're gonna build a new matrix. We're gonna call it n plus 1. We have, well, I want a dummy one, because with a dummy makes iteration much easier. So that's our pre-sum matrix. So what we do is we're gonna row by row, right? We're gonna say for row I row in enumerate matrix, right? So we go each row, and then we go each value, each column for j in enumerate, not enumerate, for j in len, no, for j and a val in enumerate row, right? So now we have each value. Then what do we say? We say prefix sum I plus 1, j plus 1, right? Because we it's going to be bigger. So plus 1 equals, right? So we go one round, it's going to be equals to the 1 plus equal, right? Plus equal to the one in front of you, which is prefix sum. Same row, but j, right? So the one in front of you. So for each j, for each column coming in, we're going to add it to the previous. Next one, we add to the previous. After this round, we have to go one more time for j. Actually, that is not correct. It should equal to this plus val. Yeah, that's the one. The previous one plus the current value. And then I want to do one more time, right, for j in range n. So first round is the prefix sum of a row. After we finish this, we need to add to the top, right? So we say for j, and then we say prefix sum I plus 1, j plus 1 is equal to, this one is going to plus equal to prefix sum I, so the previous row, and j plus 1, right? So that's that we finish. In 2 rounds, then we get the thing. Actually, I want to do this, use the other technique, which is code as we go. So make sure every step is correct. So we're going to get this example in. 0, minus 2, 3, right? And k is 2, output should be 2. I actually have both up. That's where we're doing this. 2, 2, minus 1. This one I have k is 3, returning 3. So we're going to have, there's going to be a matrix k. This is going to be max matrix k. We're not going to return anything. Return 0. Doesn't really matter. What we want now is I want to check for row, for r, in prefix sum, print r. I just want to check if it's correct. 1, 1, 2, and 1, minus 1, 3. That's correct. Yep. Okay, so I think the prefix sum we have created. Now, what we got to do is iterate through the prefix sum and calculate all possible sums that we can find. So it's going to be for I in range m, for j in range n, right? So we have I and j. So we have a current one. Again, we're going to say for I in range, for I in range what? It's going to be from the top, so from the top all the way to j, no, all the way to I, right? The top all the way to I, and for jj in range all the way to j, right? Look at that. I feel like I'm going to get time out. So I and jj, right? So I and jj, so we say the current, we just say the temp, current temp equals, so prefix sum, I plus 1 and j plus 1, right? We're going to minus prefix sum, I, and j plus 1, minus prefix sum, I plus 1, same row, right? Same row. Right? So first one is same column, right? Same column but different row, and this one is the same row but different column. All right, same row but different column. So it's gonna be jj. So minus 2, and then we're gonna plus I and jj. All right, so we're gonna do this. and then we say res equal to negative 10 to the 5th minus 1, right? That's the k. So it's a lot smaller. I'm actually going to do import math. Let's do math infinite. Math.inf, right? So what we have is here. So the temp is this, and we say res equal to max res and temp if temp is smaller or equal to k, else res. So as we don't change. If temp is smaller or equal to k, then we use temp to compare to res. And after this, I'm going to check if res is equal to k, then we immediately return res. If not, we keep going. And I say it always returns, so we don't need, so we actually need at the end return res. Alright, we're going to run this. Oh, and we passed the first one, we failed the second one. How? We said infinite, so we didn't change. So that's going to be 2, right? 2, that's going to be 4. Shouldn't this give us the value, the temp? Hold up. Put row in prefix sum and print row. 2, 4, 3, right? So I is going to be here, j is going to be here, and then I is going to be range I, and j is going to be range j. Temp equals prefix sum I plus 1, so I start with 0, so it'll be 1, and j plus 1 will be here, so prefix sum here, minus I. So I is going to be, oh, hold on. So here I think we should do 1 to n plus 1. No, I don't like that. I think we just do I plus 1. Right? We just do I plus 1 and j plus 1. That's 1 for 1, you're right. Okay. I'm going to try it, and I hope it will not time out, but I don't have high hope. This look, we have 4 levels of 4 loops. Pending, judging. Oh, yeah, it's taking a long time. Come on. No, I don't think it's passing. It's taking way longer than it's supposed to be, so I think it's gonna be timeout. Ay. Yep, so we timed out. We're passing 24 out of 39. So this is the correct solution, but it timed out. So TLE. Now the question is, how do we simplify it? So apparently we cannot do it this way, right? We cannot do it this way. So what we can do, right? What we can do is we actually do this after we finishing this. Right? That's true. We can do this after finishing this. The question is, say we have calculated all of those that I have seen before. Now we're going to add a new row to it. Right? We're adding a new row to it. So we have, think about like more dynamic programming to this. So we have all the values in the rectangle, the entire thing, right? Now, and then we have the max value. Now we're adding a new row to it, right? We add a new row to it. Now, when we add a new row to it, the only thing that changes is the new row added, right? Therefore, what we need to keep is when I add the new value. So we have all the previous values. Right? We have all the previous values, and the only thing that matters is at the bottom. So everything that reaches the bottom, right? So everything that reaches the bottom, which means all the columns, all the rows. Yeah, we are doing things that's not necessary. Well, not really. So we have. Hold on. Let me think clearly. So as I'm going through, right? As I'm going through the column, at each column, I will be able to. So once I added that, so I'll be able to calculate everything, everything, including myself. But I don't want to calculate everything, including myself, right? But that's going to take a long time. What I want is to see what is the best I can get, right? What is the best I can get? So if I have some idea of what value has occurred before, right? So which means all the values, right? So if I have a matrix, right, and we are arriving at this one, and what I want to know is like this value, right? This value, this value, this value, this value, this. Well, I all know this, and also of course this value, like this value. Every single thing that including me, which will take like if I have a list, right? If I have a list of every value, right? Of every value in order that I know, like this, but it can be calculated, right? It can calculate. It's just this value. We're gonna minus this, minus this, minus this. And minus this, and plus, plus, plus. So we can get, let's say we have a list of values ready. And then we just need to look through this list to find the one that when added to me can give me closest to k. And that will be the value in this matrix, right? And then I add a new one. But actually, I add a new column, right? Think about it. Every time we add a new column to it. So now I add a new column. What I know is everything in this thing and everything in this thing, right? I do know that if I know closest this that I can achieve, not only like that I can achieve, is the closest in there that I can achieve from this position, right? From the bottom position, the closest I can achieve from the bottom position, right? So if I know the closest I can achieve from the bottom position, the lower right position, then the question is, like if that is the most, right? Which means if I expand, I either break, right? If I break out, or but then I add myself as the new one, the new guy, add the new guy in. If I want to include the new guy, if the new guy is going to be part of this, then it has to include part of this and part of this. But why can it not be like even bigger, right? I think I passed through the first barrier. The second barrier, again, all we're looking for is k equals 2. And there will be a rectangle with sum no larger than k. Yeah, it's for sure. Sum will be there, no larger than k. But I have the value of the biggest of each one, right? I have that. If the value is, if my value is the total sum of this thing, but we have negative values, so it's, yeah, that does make things more complicated. We have negative values, which means the smaller sum might be closer. Can we reuse? Right? Can we reuse? So what we're saying is for each the bottom, right? So we have the value of basically a row iijj, right? Iijj. If you look at this, iijj, right? Iijj and plus this thing. Iijj, it does, ii is going to be here. Jj is going to be corresponding to this one. So is that a specific value? Yeah, that's like m squared n squared. That's why we got toasted. But when a new one comes, right? When a new one comes, how does the value change? So here, let's say we want to calculate this thing, right? So we minus this, but plus this one again. If I have a new one coming in, I want to calculate this. And we say with a minus this, actually it's minus this. The minus this, and plus this. So I'm going through I mean, it is possible. Well, I don't know if it's possible. No larger than k. No larger than k. So the current strategy was find all the sums, not all the sums. But apparently that's not good enough. I already try to return if it's a k, but it could be we have a sum. Yeah, the thing is we already have the sum, but then we add a new cell to the lower right, then we're adding more things to it, right? More things to it. We're adding this, and we're adding this. And we're adding this, we're adding this, and I will remove this. Which means if we have anything, it has to be rooted in this, right? Or rooted in this. So we have everything that's rooted in this in the previous, like the I minus 1 and I minus 1, j minus 1. We have everything inside that's related to this thing. And now we're adding a new one, right? We're adding a new one. Let's say we have a list of all the sums. Now we're adding a new one. We're adding a new one. So actually we have everything here. We consider rows. Now we're adding a new one. How do I quickly find out what is the largest one that I can get? I mean, I know the total, right? And I have every kind. Then I'm going to add to it. So every single thing that I'm adding from my perspective, every single thing that I'm adding from my perspective, is going to be the previous one that we already have, plus some value that I currently have, which means the previous one plus whatever height plus this, which means I might be able to find the sum in faster time if I can keep track. I can. It's just gonna be like another matrix, right? Another matrix which has have the top left corner, right? The top left corner is going to define all the rectangles, and with the top left corner defined, now we add a new column, and we know the column. We actually don't know the column, but if we do row-wise, we say we're gonna add a new row, right? We say we're gonna add a new row. Can we add a new column? If I add a new column, and that's just gonna be whatever this is, and adding that part, the column part. Can we calculate the column sum? Well, the column sum is just going to be this. Yeah, we can. This minus the whole thing, minus this, minus this. Yeah. Yes, we can. Yes, we can. We can find it. I think we can find it in OM time. Basically, we're just like adding 1, adding 2, and everything, adding 3. All right. So I just one by one we add it. But each time we add, which means if we can keep track, right? We keep track. We're going to add row by row, right? So we're going to keep track of everything that has occurred so far. Like a what? Like a but if we want to add everything to it, and that becomes the same as this one, right? Because every single time we have to go through every single one. And each column, like each row, and for each row I have to go through each column. That's exactly the same thing as this one. Which means how can we do better? how can we do better? Let's jump outside a little bit. So what we have right now is a matrix, right? A prefix matrix. How can we make use of the prefix matrix? I mean, we can go through the pre-sum matrix and look for the values that's currently larger than k, right? We can look for the value that's currently larger than k, and we say those are candidates, right? Those are candidates. And once we locate those candidates, then we're trying to find. Because if my value, if the lower left cell value is smaller than k, right? Then, well, it is still possible. Right? Just to put it that way, it was still possible to have, like, let's say, because there's a lot of negative values, therefore the overall is smaller. So the point is, it might still be possible to find that which is larger. But if we can do that way, maybe we can achieve it before we even arriving there. Yeah, let's say it's a 0, right? Let's say it's a 0, and we say we're gonna ignore it. But let's say this, yeah, we can definitely make that happen. It's a 0, but if we do these two, then we achieve it, achieve k. And all the other combinations will not achieve k. So I don't know. I do not know. I mean, we already have the prefix sum in place. What is the next leap that can help us? There will be a rectangle with sum no larger than k. We can find the sum of all rectangles in, but why it's ON squared, OM squared? I thought it's going to make it easier. It's like just going through every single one, right? If we find the sum, if we find this, and if we want to find the sum, we have to add this, add it together, add this, add it together. I'm not saving anything. I'm supposed to save. I'm supposed to save, but yeah, you are saving because I can get any rectangle sum in O1 time after the prefix sum is done. If we don't do prefix sum to get any sum of a rectangle, is going to be OMM. So that's the saving, right? But there are, in total, how many rectangles are there? I feel like it's because my logic is not correct. Am I recomputing a lot of stuff? Ending in here. I don't know, man. So we have to go through every single, because given a matrix, and if I want to extend it by a column, right? Then we're adding everything that's in there, and then we have to go through all the rows. Yeah, I have to go through all the rows, like every single one inside, marked by top left corner, right? Each top left corner is m times n. m times n total number, and then for each one of them, m times n, I need to add this value, need to add this value, need to add this value. So it's n times n times m, and then we go it for every single column. So m times n times n, that's all m n squared. Yeah, that's the same runtime as what we have here. Now larger than k. K is what? So we have a k value. What if we try to find k value and then k minus 1 to be 10 to the 5th? Be 10 to the 5th. At least we have k. So we first find k. If we rank the entire thing, right? We rank the entire thing, and then we're trying to find k. We'll put k in it. That's going to be log n to find where k is going to be located in it. And anything smaller than that we don't consider because they cannot reach k. Actually, no, that's the problem. That's the problem. It can't. It might. It might. That's the thing. It might. Any position, it might. Because we have a minus, minus, and a plus. So any position is possible. Because the matrix has negative values in it. Mine gotta be something, log n involved. It feels like a priority queue or binary search. Priority queue. What can we do if we have priority queue? We can keep the maximum value of the square of the rectangles we have encountered so far. But then what? And then add a new one, right? The maximum that we have, and if we cannot, because if it's the maximum, or like the closest to k. What do you mean by closest to k? It didn't mean anything. It feels like two sum, right? So like if we have k, like if the question is to find the rectangle that sum up to a value, right? And then we will hold this value and we'll hold this value and we'll minus this, minus the lower left, and try to see if we can find anything in the encounter so far that can give us a value that make it there, right? Isn't that how it's done? That we, because it got to end at some position, right? Then we try k, and then if we try k, we say k minus this, and for the remaining, we want to see. So how do we do it? How do we keep the values we have encountered so far, which is basically for each top left corner, right? It's gonna be a value. Each top left corner gonna be a value, but it's gonna be ended at here, right? Ended here. and when I add a new one, right, have a new column added to it, then I think we can reuse. So this one is for each one, right? It's going to be the rows. So this one, right, minus this one plus this one. If we have a new one coming in, the rows, so the row needs to, the column needs to extend, right? Column needs to extend, but the row is the same, right? Okay, so if we have all the values, like if we have this value, which is going to be, so like we represent this rectangle, right? So this one will corresponding to so it's corresponding to this whole thing minus like this thing minus this thing plus this thing. All right, so it's gonna be row above here and here and here. So when we add a new one, right, for this, all we need to do is add. We still have to, and that's the thing, we have to iterate through every single one of them. We have to iterate through every single one, like every single one, literally every single one. Every single one. In order to find, like, if at this position, what's the new value is going to be. Well, the new value is going to be whatever this value, and plus, so we're going to minus, right? Minus, because we added this one. So minus this, right? Minus this value. Yeah. So for every single one of this, it's going to be this value, and then we're going to minus this. So it's going to be OM, right? And it's going to be OMN and times OM. But we have to go through every single column as well. I have added to it. That's the problem. We have added to it. I think I can't get through. It's the second part. All right, so we close down a 1 hour mark. Let's see if we have any hints. All right, let's see if we have any hints on how to deal with the second. Like, I'm pretty sure we have the prefix, right? Yeah, it's a hard question. And all I want to know is, oh, we have a solution actually. But what is the related topic? Binary search, dynamic programming. I mean, prefix sum counts as dynamic programming. So it looks like we have to go for binary search. Okay, some binary search. But binary search requires sorted. Oh. Max sum of a rectangle. I mean, it's not sorted because of there's negative things in it. So that's why it's not sorted. Nothing is sorted in this thing. Nothing is sorted. I want to know is no larger than k. And smaller if this value, the thing is if like this value is smaller than k, right? That doesn't exclude, like this value is smaller than k, right? But this, we can add something bigger. So it doesn't exclude. Doesn't exclude. All right, we hit 1 hour mark. All right, let's go for a solution. Let's try not to. So prefix, yeah, it's all that's the thing I hit. M squared n squared won't suffice. We need to figure out a more clever. All right, approach 1. Prefix sum on 1D array using sorted container. Sorted set. Man, I always count sorted set is like type of cheating, but I think, all right, so that's so far what we read. What it says, a sorted set. A sorted set, I think we thought about this. I can do binary search if we use sorted set. Which means when we have the prefix sum, right? What we want is, how do we use sorted set? how do we use it? We have a new thing coming in, and we want to know. What do we want to know? We want to know but how do we use it? Sorted set. It basically just means we can add a new value to it in a sorted array in O log n time instead of O n time. That's what it means. How do we use it? What's the usage of a sorted array? Sorted array of what? A sorted array of all the sums. A sorted array of all the sums. And all the sums that sorted array of all the sums. I don't think it helps. Sorted array. Keep reading. And instead of a matrix, find a maximum sum of a subarray of 1D with sum smaller than k. How can we achieve this? A prefix sum. Every index I want to find a maximum possible sum subarray which ends at I. Yeah, that's true. I want to find the maximum possible sum of subarray that ends at I. If it's a 1D, all right. If it's a 1D array, I want to find the maximum that ends at I. Yes, don't think about a 2D, just 1D situation. And we have a prefix sum already, so we know the sum of any subarray. So add this array. I know the total sum, right, from start to here. And in order to find out the maximum sum that's possible to reach here, if we know, right, if we know the maximum, if I know the sum of all the subarrays, the ending right in front of me, right? If I know the sum of all subarrays, like if I'm looking at position I, if I know the sums of all the subarray ending at I minus 1, right? And I know all of them, then I can have them sorted. And for me, all I need to do is to do k minus myself, right? And I'm binary searching this and looking for the position of values that is just smaller than k minus myself, right? And then that will be the value. If I add it to it, will make me the maximum value that is no larger than x. This I can understand. But after I do this, I have to add this value to every single one, right, in order to go to the next step. That is the part I don't understand. How do I do that? A sorted container, or specified by a comparison on a sorted container, or log n, yeah? At every index I, we store the prefix sum of, at every index I, we store the prefix sums in a sorted container. Let's say at index I, the current sum from 0 to I minus 1 is S. Yes. 0 to this is S. To find maximum possible, we will want to find if a possible subarray with sum k that ends at I, and if not, then we try to find a subarray with possible sum k minus 1, and so on. That's fine. That's another way to do it. Now find a subarray with sum k. We have the equation. We know S, we know K, and X is some subarray sum ES, and give us K. To rearrange the equation, tell us if the subarray with a sum exactly equal to K, how to process it. Now we can do binary search, right? I know the binary search part. It's just after the binary search, we have, hold on. What it's saying is what? Like, as we're building up, we can copy it and then we have added everything to it. So how does that save time? Instead of searching for X, we can search for the closest. Yeah, we can do binary search. This will give us the minimum possible value so that it's closer. Yeah, that's fine. But then what? Extend the procedure. No, don't extend. You have to, wait, what's the runtime of this? M squared, n log n. I don't understand. You have a sorted array, which is the prefix sum of n minus 1, I minus 1, right? And then how do you get for I? Hold on, I think you do get I. Like, that part is not eliminated. So that means for each value, right, we need to get the prefix sum of everything. That's going to be, let's say, like for each one, we're going to have to get everything. For each one, that's O(n) squared, right? And O(n) squared. And then the look part is going to be log n. So isn't that O(n) squared log n? So we have to store it. We have to store all the prefix sums at each position, like all the prefix sum at each position. So overall, the ON, each one going to have this times, right? Because at each position, so we can think of like when we build up, right? When we build up, this is going to do this. This everyone's ON squared, right? ON squared, and then plus n log n. Yeah, that's ON squared plus n log n. If not, it'll be an ON squared. I think we can solve it by ON squared. For every one, right? We just look through everything that ends at here. Right? We have this, and then we learn everything with plus one value. But why would you use sorted set in this sense? You don't need sorted set. I think I'm still not understanding something. Okay, at every index I, we store the prefix sums in a sorted container. Let's say at index I, the current sum is S. To find a maximum possible, what it's saying is if we have this, right, then to find the maximum possible, we can use maybe log n instead of O(n), right? This would be log n. But then in the next step, possible subarray at some k that ends at I. If not, then we try to find a subarray. How do you find a number? I know we can use binary search. Still don't understand. I still don't think it can save time. And where does sorted set come into play? We're storing the prefix sum in sorted manner, which means that instead of searching for x, we can search the closest prefix that is larger or equal to x in log n using binary search. Minimum possible value so that the subarray closest to x. K, then this, and so on. Understand how to get a result. Yeah, I understand this part, but what happens? Well, okay, let's go. So what's this? The array, right? Sorted prefix sum. Hold on, that's the thing. The sorted prefix sum is the entire prefix sum that we sorted. And then I can do, hold on, the entire prefix sum that is sorted. I think I was thinking about it wrong. I thought at each location you need to have all the prefix sum associated with this in an array. And I was like, how does that save time? But no, that's not what we're talking about. What we're talking about is the sorted. We have prefix sum, right? We have prefix sum, but instead of as a laying out as it is, we have a sorted. So it's sorted prefix sum. So now, when I add my current value, I need to know, oh yeah, that makes sense now. It suddenly makes sense. We sort the prefix sum, right? We sort the prefix sum. So the prefix sum is in sorted order. Then I can do a binary search to look for the value that is bigger than k minus the current value, right? That's bigger, slightly bigger than k minus the current value. And then my value minus that, and that will be the result. Yes, that, what was I thinking earlier? I was thinking every single value, the values, that's not prefix sum. That's not prefix sum. I was thinking about every single subarray that ends at I minus 1. That's what I was thinking. Every value ending at I minus 1. And I was saying like, okay, we have every one of these and I can plus my current value. But no, that's not, that's a prefix sum. Okay, so now we have that. We just need to extend it to 2D matrix, right? So for the 2D matrix, we already have the prefix sum for everything. But we're going to save. Right? What are we going to save? What are we going to do is for each value, right? Each value. So for 1D, I have the current prefix sum. Let's say I'm going to call it x, right? Current prefix sum, and I have previous prefix sum in order: P0, P1, P2. Right? They're all in order. And now, what I want is an array sum. Like the result is going to be x minus a p, one of the things in the previous. I want this to be as close, to be smaller or equal to k, as close to k as possible. Therefore, what I need to look is for a p. So I do, right, what I do is, equal to k, right? What I do is do x minus k, right? X minus k, I want this to be smaller or equal to p. So I want to find x minus k inside the prefix sum that is smaller than, so we have x minus k, right? X minus k, that will be the value. That will be the, so we do x minus sum from this to get to k, right? If x minus this to get to k. If this thing is small, then we're going to blow up, right? So we want this to be big. So we want to find a value that is just larger than x, that's larger than x minus k. So we're going to find some value that is just larger or equal to x minus k in the sorted prefix sum. And then we get it, right? So that's 1D. Now in 2D, right, in the way that we do the prefix sum, what happens is we can sort the prefix sum, that's for sure, right? Every time we have it, we just sort it out. But it's not just simple minus, right? It's not just minus. So what I think is, what we need to do is every time, what we want, right? What we want is all the things, all the values that has occurred so far. So we have to minus one thing, minus another thing, and a plus a third thing, right? That's how we get every single one. So minus, minus, and plus, right? So for each m and n, for each m and n, for each I and j, they're going to be a value. For each I and j, they're going to be a value. So we can get those values out, right? Get those values out. And as we go for the next one, we will add a few more. Like if we have all the m and n in this situation, then we add a new one. Then we can compute new, right? We can compute new ones. And but those m and n's, I think I have the same problem as before. I do want a sorted, so I can look for the one that we want. But if I have a sorted, and I have a new one coming in, a new column coming in. If I have a new column coming in, how do I extend? Like, what's the computation like? We have to go through the entire thing. Why do I have to go through the entire thing? I already have the prefix sum. Can I reuse? Yes, you can. You can reuse. Come on, you can reuse. Everything that's occurred so far, you can reuse. The only thing that you cannot reuse. Oh, I think I have a misunderstanding. When you add a new column, all the things that we have encountered before, you can still reuse. Because it's minus, it's going to be this, this, and this. Yeah, you can still reuse. Like if I want to calculate this thing, right? It's going to be this minus this. Wait, can I reuse everything? The new prefix sum is the entire thing, right? And in order to calculate everything ending in here, what I need is, like if I calculate this thing, I'm gonna have to remove this, right? Remove this minus this plus. Okay, so every single one will be minus this plus this, right? For every single one minus this plus this. So when we add a new one, all the previous one, that doesn't work anymore, right? It doesn't work anymore. We have to recompute. So for every single row added to it, we have to recompute the entire thing. We have to compute the entire thing. So for each row, for each column, that's m times n already. And then to recompute the entire thing, I think I'm falling back into the trap again. We shall be able to, like every time we're talking about O n log n to get to the one we want instead of O n squared. But now what I'm saying is we have to do OM for every single one. Once we do, we'll get all the rows. I still don't get it. How do we avoid, like we have the prefix, okay, we have the prefix sum, right? And I just need to minus a prefix sum to get to the one. And this one, I have prefix sum. I have to minus a prefix sum. I have to minus 2 prefix sum and plus 1 and then get it. But that's 3 values, right? That's 3 values. That's 3 values. How do we handle 3 values? The 3 values are oriented differently. All right, I have to keep reading. Okay, I go past the first round. So how do we do in a 2D? Converting each 2D matrix to a 1D array, and then running the previous program. A 2D matrix into a 1D array. You just add them together. We have a 3 by 5. We'll start by finding the maximum result for all 1 times 5 each row. Next, we want to find the maximum possible results for all rectangles having 2. Okay. We'll find a row by row. The maximum results for all 1 by 5 arrays each row. And then we want to find the maximum result for all rectangles of height 2. So we convert each 2 by 5 into a 1 by 5 by summing each column. Can be converted into a 1 by 5. So we go 1 and then 2 and then 3. So we know it's going to be O1 log n for each row. And then for 2 rows, then we can compute the 2 rows, sum of every 2 rows, right? The sum of every 2 rows. But the sum of every 2 rows, we can do that in our current matrix. Can we do that? Yes, we can. Yes, we can. We have 2 rows. So we turn 2 rows into that is going to be very easy, right? If we want to use 2 rows, I just need to go through every single one. Like each column, right? Each column, we want the column. Each column, that means just for each one of them, for each one, we're going to get the sum of the column, right? Get the sum of the column, which is this one minus this minus this plus this, right? So we're going to get OM. So OMN, we build the entire thing, and then for 1 to M, right? So that's M, and for each one is going to be for 1 row and log n, and then for 2 rows. Now for 2 rows, we need to build up the prefix sum again, right? How do we build up the prefix sum? Building up for this and this and this. For each one is going to be O1 to build up this, build up this, build up this. So the building up part is going to be, that's O1 log n, right? So, which means we're going to go OM is the total number of rows, like 2 rows, 3 rows, 4, 5, such all the way to that, right? And for each one of them, we have to go m times. That's OM squared, right? And then for each one is n log n. So that's m squared n log n. I think that is m squared n log n. So it avoids my question of have to calculate everything. So we're not doing that. Why does this save time? Because we're considering ON. Now we're considering a multi-row matrix as a single row matrix, right? And once we do that, it's going to reduce. Okay, I understand this first solution. So let's try to code it ourselves. So this is the same, right? This is going to be the prefix sum. We're going to use that. But then will come, so num rows, right? Num rows in range 1. We're going to go 1 row all the way to n rows, right? And inside here, the num rows, so for 1 row, for each number of rows, we have to go through for I, again, in range. Now, that's going to be num rows, right? Num rows going to be the starting point, right? Num rows. What's I? I is going to be, I'm going to go call num rows minus 1. So I want this to be the actual index of the matrix. So num rows minus 1, all right? Num rows minus 1 is the starting point, and then we go all the way down to the end, which is m. So I in this, right? And then that's the row, and for each j, and for j in range n, we need a sorted set. Do I have it? I think I installed it. Let me see. Oh, hold on. I might have installed it here. Not sorted. Not sorted set. It's going to be sorted array, right? Oh, sorted set. We need sorted set. It's not array. Sorted container. Table of contents. Yeah, I remember recommending this to Python bytes. So, do we have it? Import sorted. Yes, I do. Sorted containers. Sorted set. Okay, let's go take a look. Sorted set. What's the API? Sorted set. Key iter add on login time. Discard. Clear, pop, remove, difference, intersection, symmetry, union, update, count. Wait, can I do binary search in this? What, bisect? Do I have bisect? Sorted containers, sorted key list, sorted list bisect. In sorted list. It's in sorted list. But now we're talking about sorted. So we can use sorted list, right? See, sorted list has bisect. The sorted container doesn't have bisect. It's also called add. Yeah, we don't need to use sorted. Okay, use this because it has bisect in it, built into it. Okay, so, and we cannot run it directly. We have to run it. Where is my thing? Come on, here. So we're gonna say from sorted container. Yeah, container containers. Oh, they have. Oh, wait. Sorted list methods available. Oh, it's also available. Okay, so sorted set can do that as well. So it's containers from this import sorted list, right? You probably complain it doesn't exist. Oh, did I install it globally? Huh, maybe. Anyway, so we're gonna say we create a new one, or I think it has a clear method, right? Do we have a clear method? Scar clear, yeah. So we can just put it on the outside. Call it sorted prefix. Sorted P-sum equals sorted list. No, nah, it's not sorted list, man. It's sorted set. Right, so we're gonna do sorted set, and then add a for each the nums in this. So we're gonna say sorted dot append, not dot add, right? Dot add what? So we have a j, right? So we just need to add the sum of the column, which can be acquired by prefix sum I plus 1, j plus 1, right? Minus prefix sum. It's going to be the entire column. The entire column. No, it's not entire. It's the, hold on. It's going to be the prefix sum. Minus I plus 1, same row, but it's going to be j, right? Same row, but j. So we're going to remove that. And we're going to also remove prefix sum. Same column, so it's going to be j plus 1, right? For the row is the thing. The row is going to be the current row minus num rows, right? So if the current row is 2, minus 1 minus 2, that shall do it. Because we want to go up. So we want to include 2 rows, right? And I'm here. So minus 1 and minus 2 shall do. Which I think it's I have to add 1 plus 1 as well. Because it's I minus num of rows. I plus 1. This is my current position is I plus 1. Right? Current position is I plus 1. So I plus 1 and minus the number of rows. Right? If I want to put 2 rows, we're minus 1 and minus 2, and then go to the top. So we're going to minus all these and then plus prefix sum. So that will be the top left corner, which is going to be j, right? J and I minus num rows plus 1. So that is the thing we're going to add, right? So once I add it, we have sorted P-sum, we add it, right? Then I can compute, which is, we're going to say, what do we say? K minus current value. What is the current value? So j in range n, right? J in range n would add every single one, the prefix sum. This is the prefix sum. So we add the prefix sum into it. And after we add it into it, then what happens? Now we have to first do it and then add it into it. So what we say is when we encounter a thing, we're gonna do a sort, right? I'll do a sort. I'm going to do a sort for something larger. So we're going to do this bisect right index insert value and the sort list. Yeah, the right. So what we're going to do is sorted. We're going to do sorted sum dot bisect right the value. Value can be k minus which is just like the current sum is going to equal to, so we're going to put this whole thing, right, current sum is this. So we have the current sum, and then it's going to be the k, no, it's going to be current sum minus k. We're going to find a value that's slightly larger than this, right? So we're going to say return an index. So index equals this, right? And then we're going to say if it's equal, and then we're going to go into previous. So if the value comes out is 0, what if it's a 0? That means everything in it is larger than this. And we just return the 0, right? We just return the 0. Wait, how do we access the value in it? We can add, we can discard, we can call it. Yeah, we can directly call it. So we say, or do we add it first? We can add it first. And then, yeah, we can add it first actually. Yeah, we can add it first. Because it's not going to matter too much. This will be, yeah, it's going to be minus, yeah, we can add it. We can add the current sum, right? We add the current sum to sort this, and then we look for it. And then whatever value we find, right, whatever value we find, we're going to check. Or whatever value we find itself will be the right one. But if minus 1 is the same, then we need to go to minus 1, right? Otherwise, we stay at the index value. The index value is supposed to be something that's larger. That's what we want, something that's larger than this, which means current sum minus this will be smaller. So in the check is to say if, right, if we say if index, and also keep the result, right? Result minus math dot inf. So we say if index, because we do bisect right. So we say if sorted p sum index minus 1 is equal to current sum minus k, then we just return k, because that means we have found one that can reach k, and we don't have to k continue. If not, then res equals max res and current sum minus sorted p sum index. What if it's bigger? I mean, this could be out of range, right? This could be out of range. Well, if it's out of range, then yeah, we have to consider the situation where it is out of range. And nothing is bigger than this, right? So everything is smaller than current sum minus k, which means my value will be larger than k. So if everybody is smaller and I am the biggest, then I should not include it, which means we have to have another one. If index is equal to, we call len, yeah, equal to len, sorted this, no, if it's smaller, then we perform this operation. Right, and then this part is log n, on log n, right? On log n, on squared. And we need to return the rest at the end. Alright, let's see. I'm not sure if I've installed it. No, I have not installed it, so I have to do it here. So it's going to be front Python 3, run it. So we passed the first, but we failed the second. And we got a 0. That is interesting. How do we get to 0? We know the p sum is right. This is right. The num rows 1. In one row, right? 0 to 1 is 1, 0. And then current sum. That's 0. I don't even see 0 in here. What is happening? What is happening here? Let's comment out this and run it again. So let's print out the current sum. Right? Let's print out the current sum. Let's see what happened. Let's print out the sorted. No, I want to print out the current sum. Just to make sure this one is correct. Oh, I shouldn't do it this way. Do it this way. So we have 2 minus 1. That is not right. That is not correct. The current sum shall be, oh, that is actually correct. And what is wrong is it's not a cumulative sum. I think I understand it wrong. No. We need a cumulative sum, which means, nah. We just need to current this minus I plus 1j. No, we don't need to minus this thing. Because that is the column. We don't want a column. We want a cumulative sum. So we just need to minus this. And we don't have to plus anything. So, oh, that actually makes it much easier. I think that, wrong. Well, we're almost there. So 2, 4, 3. That's correct on this, but why the result is not the right thing? If we go 2, 4, 3, and then we do a bisect, the bisect can give us a 0, and we'll look for a 0 in the prefix sum. It's going to be hold on. What are we looking for? We're looking for myself minus this equal to a k. Therefore, say we want to look for a current sum minus k. Why is 0 not part of it? Because we are wrong. Because we have to add 0 to it. Now to add 0 to it, all we need to do is have the first is here. We need to say sorted this dot add 0. That one go through, and I also forgot to sort it this dot clear. Now we pass because we added 0 to it. Okay. Let's copy this answer. Paste it in here. No, actually, I wouldn't do it here because I have a test case, another test case that we failed earlier. Let's see. Copy here. Let's try to run it. Sorted set is not defined because we forgot to do this. We have to import it. I mean, this means sorted set is okay for use, but actually, even if it's okay for use, I wasn't able to figure out because the way I was thinking is not correct. It's still slow, right? It's still slow, but I think this will pass. Pending, judging. It's probably take 3 seconds, 4 seconds. That's a long judging. Oh, we got a wrong answer. Huh. 2 minus 1. Okay. So, same 2 minus 1. So we have 2 minus 1, but we want a 0. It cannot be larger than 0 and minus 1. I think it's because no, it shouldn't be, because we didn't involve answer minus 1. Okay, so let's do these two. What do we do? Same thing. We're gonna print out for everyone sum, right? So we're gonna print current sum, and I'm gonna print sorted sum. Like, let's just see what happened. Oh, I spelled it wrong. Print 2 sorted 0 2, and I said we found the answer. Oh, we found the answer. So we have a 0 in it, right? Then we have a 2, right? So we have 2 in it. And then the k, current sum minus k, bisect right. Current sum is 2. K is 0, right? K is 0. So 2 minus 0 is 2. So we're going to look for something that's larger than 2. Ah, that's myself. That's myself. So shouldn't do it this way. We should add it at the end. There we go. Yeah, we should add it at the end. Let's also check the other two. Yeah, so this means I think that the only thing we need to change is to add this line. Yeah, because we have the 0 in it, so it's actually fine. And we add it here. Then we run the code again. It'll take like 2 seconds to run this. Okay, so we'll submit again. Pending, judging, 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 judging. Yeah, this, oh my god, it's like what, 5 seconds? Oh, 8%. 8%, 6 seconds. 8% ranking. All right, with the help of the solution we are able to use sorted set to solve this problem. I mean, the key is to realize that to first understand a simpler question, simpler problem. How to find the max sum that is smaller than k in a 1D array. It can be solved in O n log n time using sorted set. Right, this can be sorted set. So using sorted set and prefix sum. Extending to a 2D array, the trick is to consider rectangles of 1 row, 2 rows, 3 rows, etc. And for each rectangle, we reduce it to a 1D array by adding all the columns together. Then the problem becomes a 1D array problem that can be solved in O n log n time, right? To compute, so to acquire each compressed rectangle, we need om squared time. Therefore, the total time complexity is O n squared n log n. I mean, even like after learning that we can use sorted set or sorted list, this is still like tough because I mean I know about the prefix, right? I know about the prefix sum for a 2D array, but then to simplify the problem into 1D array, which can be solved in O n log n, is a leap forward that I wasn't able to figure out. And then, like, even if I know that, which ironically it took me a while to understand, it still hinges on the realization that we can convert a 2D array into 1D by combining the rows together. Okay, so this solution we pass. Let's keep going. We haven't recorded at runtime. So this is going to be O. Yeah, we already talked about it. So we just need to take it 6,320 milliseconds. 8% ranking. All right. So this one we pass. So the next one. So we pass this. Now we go to solution. Yeah, this is a pretty Yeah, like I always say, like hard question, hard problem contains two leaps, right? Two leaps. Now we were able to figure out the first leap, which is the 2D array, the prefix sum, but the second leap was beyond us. So good, first one. Oh, Java. Yeah, I mean, actually write it out. It's not that. It's not that much. It's not that much. Yeah, I don't think the Java will simplify anyway. It's called tree set. It's called tree set. How about this? Sorted sum. Container to store sorted prefix. And this is the right way to do it, right? I'm actually not quite sure. I think so. Current sum, we do a binary search, and then uh, we find this. I didn't see it checks for anything. Yeah, I don't see a check for anything. Just set it up, right? And then two of this. Oh, update result. I think it has a 1D is here. Uh-huh. Ah, yeah, yeah. So, okay, that's fine. That's fine. You put the two together. All right. Understand this? Large number of rows can come. I mean, we can just like rotate it. Right? We can rotate it. I think it's the same thing. Maybe it can run faster. Are you saying it runs faster? Yeah, it does run faster. Minimum mn squared, maximum mn, and the log max. Yeah, I think it's just rotate it. You notice that in the previous approach, we get the most time to iterate over and combine. It's obvious that if the number of rows increases, the time significantly. Yeah, to get around this, no specific reason in the previous approach perform a row-wise. Exactly. We can perform a column-wise combination. Yeah, we just rotate it. All the m will turn into I and j. Just roll. Well, it will be a little bit mind gymnastics to rotate, but it's not that hard, I think. We can do it. Yeah, we can transpose. Yeah, that's the one I was thinking about. We can just transpose it. Transpose takes OMN, so it doesn't really matter. So we can just transpose and then redo the first. Yeah, I would just transpose it. All right, Cadence. Okay, Cadence is the max possible sum of a subarray in ON time. That's what we want, right? The max for a 1D array. If we use binary search, that's ON log n. But Cadence can do an ON. How does Cadence work? Oh my god, that was the very first thing that the algorithm class I had, the professor gave us, the Cadence algorithm. I think we record, right? We record the global max and the local max. And the local max is the maximum sum that can be achieved ending at a certain index. So when we go to the next index, we can choose, right? We add it, so we find the max that can end at myself. And so I add to the previous one, the max of the previous one, to see if that is going to be bigger than myself or not. Then, yes, I think that's Cadence algorithm. So we keep track of the maximum value ending at each index. And we also update the global max. But the thing here is smaller or equal to k. How do we do smaller or equal to k? Where the maximum value that I can achieve at each one. And then I say plus myself. Let's keep reading. One year we try to find the result for. We can first run Cadence on it and get the maximum possible. Okay. If this result is smaller than k, we can simply skip running our initial algorithm as we already have the maximum possible. This will help us significantly reducing runtime with max subarray sum. Take O(n). Oh, so we just run it once. It's going to be O(n) regardless, right? It's going to be O(n) regardless. We run it once, and if we're good with it, then that's it. Yeah, if the maximum subarray value is going to be smaller or equal to k, then we're good with it. If it's not, then we do it again. Let's add extra Cadence. Probably it'd be best if we write a subroutine to calculate the Cadence. It's the same. People are asking these questions. Why does n squared does not pass? Well, come on. The purpose is not to pass, right? The purpose of us doing this is not to pass the LeetCode online judge, right? That's not the purpose. The purpose is to learn. If you're complaining that why my brute force solution doesn't pass, it looks fast enough. But no, it's not fast enough because it's brute force. Right? The purpose is to learn new methods and improve yourself. We can add Cadence. Let's add Cadence. It's just, oh yeah, the beauty of this is, we are turning the problem into a 1D, right? Into a 1D problem. So we can use all types of magic that's available in 1D array. Why do I add it here? Should be added. Also, let's say TLE brute force. I can't believe that we already have a prefix sum and it is still brute force. All right, so this is solution number 3. So this is going to be add Cadence. Add Cadence also. So what we're gonna do? We just def Cadence. Cadence we need. What do we need in Cadence? We need an array. But notice, Cadence, it cannot be sorted array, right? It's not a sorted array. It's a regular array. That is going to be an issue. Hold on. It's not just simply adding a house. We don't have, right? So what I do is every time I get the prefix sum, and then I run the algorithm, right? If I don't, I get it. I need to push that's still O(n) log n. I think let me see here. So what we're saying is update, and we can say update. Wait, which one is Cadence? This is Cadence. So we have a Cadence, we have update. So you run the Cadence. If it's good, then we're good. If not, Ah, I see what you're doing there. I see what you're doing there. This is actually smarter. Huh. Maybe. Maybe. Okay. So they produce the entire thing, right? What do we do? I mean, we go through, right? We have to go through the entire thing. We get the prefix sum. Oh, hold on. If you do Cardane, that's not prefix sum. That's the actual thing. Ah, now I see. Now I see. We're not using prefix sum. We only do prefix sum afterwards. Got it. So Cardane, we need to pass in an array, call it that, list of integer, and we need to return a max value to the integer. So we have a result is going to be global max minus math.int, and we're going to have a local max minus math.int, right? And I will just say for I, a in enumerate, all right? Actually, yeah, that's fine. We say if I is 0, right? Then we say res log equals a and a. Else, then we say log local max is going to equal to, not local max, we're going to say, actually, we don't need the local max. We just need, this is going to be array 0, right? For I in range 1 to len array. So we say array I equal to the max of array I, which is I don't include the previous, or array I plus array I minus 1, right? The max of the two. Once I get it, the rest equals max rest array I. Yeah, that's Cardane. And then we return the rest, right? So we go blah, 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 blah. Now, in here, we will first acquire, we're going to first acquire an array, right? The array of not pre-sum, okay? Not pre-sum, but it's going to be just the thing, the column, which means we're going to have to minus prefix sum. I think it's the same row, but it'll be j, and plus prefix sum I plus 1. No. I minus num rows plus 1 and j, right, and j. Plus 1 j. And then, I'm pretty sure that in a test case, they will have like a long thing table, so you have to do a little transpose if necessary. So I think that is this, right? And that's not current, that's the column sum. And we are not going to do this yet. Right? We're not going to do this yet, so we're just going to say column sums equals just an array, regular old array, and we're just going to do for j in this, we can do it this way. Put it here, right? For j in range n. So we get column sum, and then we run max sum equals Cadence column sum. And we say if max sum is smaller, if max sum is equal to k, then we return k. If max sum is smaller than k, then res equals max sum, and it continue, right? Otherwise, now we're gonna do the other thing. Otherwise, we're gonna do out of k, and this is gonna be for s in CS column sum in column sums, right? And then we say column sums in column sums. Current sum is equal to CS plus sorted I minus 1, right? But here I need I in enumerate, right? Enumerate this, and this is actually not I minus 1, it's going to be I. And then index equals this, and then if this, return, otherwise, if this, do this, and then this add current sum. I'm going to go, yeah. Actually, it's going to be minus 1, the last one, right? Yeah. But we have clear. I actually don't know. Clear, yeah, let's just do I. I see. So we just create a new one. Yeah, we just create a new one. It's equal to sorted set, right? Sorted set 0. And we don't need here. And we don't need clear. And this one we just can call minus 1. And we don't need enumerate here either. We just call CS. Okay, so that's our solution 3. Okay, so we're going to test it. Oh, the last one failed. Answer is minus 1, and my result is minus inf. How is that possible? Max sum to that's gonna be 4. Max sum is 4, right? All right, let's first check. Let's print column sum. Column sums. 2 minus 1. Yeah, that's column sum 2 minus. Actually, I don't need this. These two pass. Column sum 2 minus 1. That's fine. And then sorted set. We get a set. And actually, we can also check on max sum. Your dressing is inside the fridge. So max sum fine. So the problem is here, but I use the same one. So for each this current sum, and then we try to find it, and then I say sorted sum, add current sum. Why is this one not correct? The current sum is correct, right? Let's see the current sum. Current sum. Oh, 269. That is not correct. How did 269 happen? Current sum equals CS column sum plus sorted P sum minus 1. Alright, so we need to have sorted P sum and CS. We check out all three. So sorted P sum is 0, CS is 2, current sum is 2, yeah, and then we have 4. Huh? How CS is 4? Oh, shoot! I think I know why. Because I changed the value here. Change the value. That's why. Oh, man. Yup. Change the value. Alright, so you should not change the value. Come on, man. You should not change the value. What do? We don't have to change the value. We just need a local. Yeah, we just need a local is this. I'll call it pre. You know, why do you change? I don't understand. So all we need to do is, right, array I equals max, array I, or array I plus pre. And then rest equals, no, that's not array I. That's going to be pre equals this, right? And then I don't have to change anything. And then we pass. It was on me. This was on me. This was completely on me. I didn't write the Cadence the right way. Now we fail on the first two. What the hell? How? How the first two fail? Nothing's changed. I mean, I changed Cadence. Answer is 2. I got 1. What? This is bonkers. This is bonkers. Alright, let's take a look again. We have to see if so we're gonna go column sums and then we go Cadence max sum. Just try to see if these two is correct. This is correct, right? For each array I coming up, I'm gonna add pre, which is the max. Oh, this should be pre. That's the last mistake, I hope. Okay, let's not print out. Let's just do all of them again. There we go. It's still the Cadence. The Cadence. All right. Add the Cadence. Let's see if this one's faster. Oh, this was long. Dang, it's a long 43 lines. We have the Cadence, we have this. Submit. Pending. Oh, what the hell? I forgot every single time. Every single time. Come on. I wonder if sorted list will actually be faster. Don't know. Oh, we got a wrong answer. How? How did we get a wrong answer? It doesn't make any sense. Come on, man. Output 3, expected 2. What the hell? Must be something here. It gotta be something here, right? j in range n. J in range n, for each one, I do I minus j plus 1, or I plus 1, the same row, and then j, right? Same row, j, that's the entire thing of this, and then j plus 1 of this, and then what we need to do is j and I minus num rows plus 1. That seems right to me. And we have max sum is 3. Maybe it's here. Let's say it's the max sum. Is that problem with Cadence again? We add first one, right? And then every second I will be myself, or myself plus the previous one. And then that's going to be the current max ending at myself. And then I can compare and return rest. What is the problem with this one? Oh, this one wrong. Let's see if the Cadence, I think the Cadence is correct. Current max and this current max plus num Cadence, max equals max and current max. Yeah, that is exactly what I did. Well, not exactly, because they start from every single one. I start from, but that's fine. Right? That's fine. That shouldn't matter. Are you telling me that my Cadence is wrong again? Oh no, hold on. What was the test case we failed? Here. I don't think so. I don't think so. So what you're saying is, if we change this into rest_pre equals math.inf and 0, then for a in array, pre equals max a plus pre, rest equals max rest and pre, and return rest. You're telling me that this one will return correct answer? No, it does not. So my original one is fine, but I agree this one does look better though. Does look better though. Alright, so the problem must be with here, which I don't understand. We do it exactly the same thing. Come on. Come on. Alright, we have to investigate. Let's just investigate here. So how do we investigate? We need to know if a column sum is correct. Let's remove one row just to see if this one helps. That's wrong already. Output is 3. Interesting. How about only 1? Oh, hold on. Oh, yes. What if 1? So 1 is correct, right? So if 1 is correct, we find out that it's going to be adding together as 2, right? But when we add a row, right? So we add a row, and then we have issue. The row is minus 3, minus 4, 4, and 5. Why do we have issue after we add 1? So what we can do is print out, right? So I in range num rows minus 1. And I arrange, then I get column sums. So again, I think I want to print out the column sums and max sum from Cadence, just to make sure everything is correct. If we do this, we're going to have two column sums, right? So the column sums from this, right? So both does not give us the result we want. Hold on. That is not correct. How is the maximum 5? How is this maximum 9? Oh, this is 9. This is 5. This is 10. Okay, that is correct. Cadence is correct. And we're going to check on this, see if 2 minus 8, 1, and 9. That is correct, right? That is correct. And then we do prefix sum on this thing, right? The prefix sum on this thing. It's going to be 2 minus 6 minus 5 and 4, right? It's going to be minus 3 minus 7 minus 3 and 2. And this one is 2 minus 6 minus 5 and 4. So when we go through this, for CS, we get it, right? We get index is going to be, we need to add a 0 to it, just in case. Current sum. So we say sorted p sum, ID, the current sum, right, minus k. And of course this, if index smaller than length, smaller than length, then after all that, I add the current sum into it. Okay, so this one's fine. I don't think this is the problem. So what I'm going to do is I'm going to go through this. How? I'm going to print out the current sum, right? Print out the current sum and sorted p sum. Right, print this out. Alright, so current sum, so 1, 2, 3, 4, 1 minus 3 minus 4, 4, 9. We have that. And 2 minus 6 minus 3. That is not right. Because what we have is 2 minus 8, 1, and 9. How is the prefix sum becomes 2 minus 6 and 3? Where is 1? Did we skip 1? Yo, this is not right. Hold up. We need to have a little talk here. So I'm going to go print CS as well. What happened? 2 minus 8. Ah, I see. That is the problem. We cannot do it here. It can now do sorted. Find out where the problem is. So it has to be column sum. Screw it. Screw it. I'm gonna do it from iter-tools, import. I think it's accumulate. Right? I think it's accumulate. I screw this. So we'll just say for current sum in accumulate column sums. This is like serious. Just screw this. I'm not going this way. Kind of deal. There we go. All right. Pending, judging, keep judging, keep judging. There we go. 3 seconds. 3 seconds. My God. So Cadence does go faster because we are eliminating a lot of the computation. Right? This is good, Cadence, but we did use one more thing from iter-tools, not unit test. Iter-tools import accumulate. Should have thought about accumulate before. And actually, with that, this can be slightly easier to do. Actually, no, I don't think so. This one is already pretty simple. All right, that's it. Wow, it's pretty hard. Pretty hard. But I like the solutions. Clean and concise. Sorted container. Yeah. Time complexity n squared O n squared. Do you have the sorted? Wait, count range sum. Different function for count range sum. Doesn't matter. All right, that's it. I think the idea, the take-home message is, I have multiple. You have a rectangle, right? You're always trying to shrink it down to 1D so we can simplify the problem. Shrink a 2D matrix into 1D and then solve it in 1D, but we just shrink the 2D matrix of all number of rows, right? That helps. All right, that's it for today. How long? 2.5 hours. It's not too bad. I will see you guys tomorrow. Another difficult question. Adios.